At last, we've made it to big idea number 6, equilibrium, and this is large enough that we're actually going to have to split it into 2 sections. So let's just cover generic equilibrium concepts first. We'll do some solubility, Q, Le Chatelier, what is equilibrium, and then the second video in the series will be acids and bases and buffers. So get started here. Equilibrium, just general equilibrium. When we have balanced equations, they do not always go to completion. They go to equilibrium. Generically, we can kind of think about it like a percentage. It's like, does it go 50%? Does it go... combustion reactions actually will go to completion. We call that like 100%. If it's more than 50%, we have more products. If it's less than 50%, we have more reactants. And it's more complicated than that, but that's just a generic idea to think about it. So we have this balanced equation here, and it is not going to go to completion. So we're going to get an equilibrium constant K, which tells us the ratio of products to reactants and how far right or left the reaction actually goes, which products or reactants are favored. So if we start out and we had a problem and said, okay, maybe I have 1 mole of this, of each reactant. We don't have anything to start with. We kind of set up this generic ice chart. And if our balanced equation is there, we can kind of joke around and call it a rice chart because we have our reaction up top. And then we look at the change in the equilibrium. Now the coefficients are important to come down here, and we miss a lot of this with acids and bases because all their coefficients are 1. But just normal equilibrium problems, we've got a 2x. Here we're losing 3x. We're going down because these are 1 and these are 0. So I know I'm going to proceed to the right in this scenario. I'm going to gain 2x over here, and I'm going to gain 2 more x over there. Now if we had the equilibrium constant, if we actually had the value for it, that would be enough for us to plug into our calculators and figure out what the solution is. And you're allowed to use the solver on your calculator instead of doing like full quadratic equations. But our products over reactants raised to their coefficients, we get water, if this is water gas, these are all in the gas phase, I didn't write that in, squared, SO2 squared over H2S squared over oxygen gas to the 3rd power. So if we had the numerical value, we could calculate x, figure out what the equilibrium concentrations are for all of these things. But sometimes they give us different problems. They say, okay, I have these 2 things in an evacuated container. Let's highlight those in a different color. I've got these 2 reactants in an evacuated container, which implies that I have 0 of my products. And then they might say something like, oh, and at the end I have 0.6 moles of my SO2 gas measured. And that's all they give you. But if you set up your ice chart, that's enough to solve the problem, because we're looking and we say 0 plus 2x is 0.6. Guess what? X is 0.3. And that gives me enough to say that my water is going to be 2 times 0.3. That'll be 0.6. 1 minus 3 times 0.3, 0.9. So I'll have 0.1 left over, and 1 minus 2 times 0.3, 0.6, we'll have 0.4 left over. So then once I have all these equilibrium concentrations, I could calculate K if it was not given to us. So there's lots of ways to fill in these gaps, lots of ways to ask these questions. And then in another sense, we could also get, if these are all gases, they could give it to us in pressures. The notation is slightly different, but the math is the exact same. We say the pressure of H2O squared times the pressure of SO2 squared over the pressure of H2S squared times the pressure of O2 cubed. Products of a reactants raised to their coefficients. K equilibrium and Kp are not the same thing. There is this generic equation which states that Kp is equal to Kc, and Kc is the same as K equilibrium, the concentration one. Those are all the same thing, times the gas constant times the temperature raised to the change in moles of gas. So this equation is not on your equation sheet. You're probably not going to have to do any calculations with it. However, this concept where Kp and Kc actually measure different things, they are different. The ratios are still going to work as long as you're in one or the other, but there's this little catch here. There is a time when they are the exact same number. If the change in moles of gas is 0, RT to the 0 power is just 1. If this term happens to go away, you have Kp is equal to Kc. So there's this little catch that maybe conceptually we want to know that they measure different things, but it's possible for them to be the same number as well. So simple equilibrium, filling out ice charts and looking at how far to completion they go. The next thing we'll touch on here is going to be solubility, KSPs, the solubility product. And it's important to define solubility when a question says the solubility of this certain salt is such and such. Solubility is defined as X in our ice charts. That's what they're giving you. They're giving you the value of X. So when they say calculate the solubility, they want you to calculate X. If they give you the solubility, then you can plug it in and calculate a myriad of other things. So simple equation again, let's look at a solubility equation. Calcium fluoride, solid, turns into calcium 2+, aqueous plus 2, fluorine minus is aqueous. The ice charts here are important for solubility because solids will never appear in the KSP expression. So the KSP will never have the solids with it, and the solids are always on the reactant side because we're talking about how these solids dissolve. That's how the solubility product is defined. It's the calcium ion concentration times the fluoride ion concentration squared, because that one has a coefficient of 2. So they never give you starting amounts of the solids because the solids don't matter. So they'll just say calculate the concentration of calcium fluoride. And you know you have 0 here. We know that they're going to go up by X because we're starting with 0. So they're just going to end, if we don't have anything to start with and the solids don't matter, we just have those amounts and we can kind of fill that in randomly. Really without much information. We can do all of this without a real problem to guide us. When we plug that in, calcium is going to be X, fluorine is going to be 2x squared. We see that we get 4x to the 3rd power. That's our KSP. So we can solve for either if they had the solubility, we could solve for KSP, or if they gave us the KSP, we could solve for the solubility. Within that world, we also have common ions, where the solubility changes if you have a starting amount of something else. So this 0 and 0 calcium fluoride, they don't have to be 0. If I had pure water, it would be 0, but we could get a question that says, what is the solubility in 2.0 molar NaF? What does sodium fluoride have to do with calcium fluoride? It has a common ion of fluorine. So my fluorine in this case would not be 0. My fluorine would be 2 molar. And if this dissociated more than once, if this was something that was like had 2 fluorines on it, we'd have to double that. Watch out for dissociation. But my fluorine would not be 0. It would be 2 molar. So it would be 2 molar plus 2x, and then those x's are always going to be insignificant. You don't have to worry about it. When you have common ions, x is insignificant. So for whatever term you have a starting amount of, you do not need to subtract the x's. The initial concentration is the final concentration. Okay, you're not going to need to worry about that concentration. So we definitely want to have common ions worked out as well. We can also have scenarios where our products do not have nothing to begin with. We have a little bit of everything. Those are our Q calculations. And I like to put a little initial sign here. We use that 0 sign to say that those represent the initial concentrations. So Q is my initial. Spelling being challenging. Those are our initial molarities. So the math is the exact same thing. If we were to compare this to our ice chart from the very first example, my Q calculation, my Q ice chart would say, okay, Q is going to be equal to the initial H2O times the initial SO2, and both of those are squared. It's still products over reactants raised to their coefficients over the initial H2S squared times the initial O2 cubed. Those are just initial concentrations instead of the equilibrium. When we would use that would be, if we go back to our first problem, we had 1 mole of my reactants and no products. Well, what if I had all 4 of them? I had 1 mole of these and then 1 mole of these also. We don't know if I'm going to subtract from the reactants or subtract from the products because we don't know where the equilibrium lies because we have everything. If you have 0 on one side, you know you have to shift that direction. But if we don't have 0, we have to figure out first which way we shift by calculating Q and comparing it to K. And if our Q value is greater than the K value, that means initially we have more product than we need because it's product over reactants. So my bigger number has more products. And this is my initial set of conditions. So initially I have too much product. We need to shift left. Okay, because we have too much product in this scenario. If Q were equal to K and they came out to be the same number, well, the problem's over. You are at equilibrium. Those initials are not really initials, they're finals as well. That is the equilibrium, nothing will change. If my Q, however, happens to be lower than K, products over reactants, now my smaller number, Q, I have too much reactants. If the bigger number's in the denominator, it's going to be a smaller number. So initially, I have too much reactants. In order to make that number larger so that it equals K at the end, I need to shift right. So these are Le Chatelier type problems. I will subtract from the reactants, make more products, and try to get to equilibrium that way. So those are our Q calculations. We can do that with KSPs. We can do that with normal equilibrium, acids and bases, whatever. When we do that with KSPs, we have an added layer of some stoichiometry problems. If you have to actually calculate the finals, if you have both of them, remember we kind of you treat it as a limiting reactant, take one of them down to 0, and then do a totally new ice problem with the remainder of your second one, your excess reactant, as a common ion. So you'd be starting with 0 of one and then a common ion of the second one to figure how much of your limiting reactant really is left over. Because it can't be 0. That's the point of equilibrium. None of these concentrations are 0 at the end. Last part here then. Let's get into Le Chatelier, and then we'll wrap up part 1. Le Chatelier is kind of, we just casually we call it an opposite game. Any stress that's done to the system, we want to undo that stress. So if my stress was concentration, we add more of a substance or we remove a substance, then we need to, the reaction will shift left or right to remove what you added. So if I added some reactants, I'll shift right and make more products. If I add more products, I'll shift left and make more reactants. Pretty straightforward. It's the removing category, removing concentration, that gets a little bit tricky because we can't just take something out. There is always a how. How you take something out is usually done in a side reaction, and it's not as explicit as adding something which you can directly control. So if we had the dissociation, for example, of sodium chloride dissociates into sodium and chlorine, sodium ions and chlorine ions, sodium chloride solid, and then I have aqueous sodium and chlorine ions. And then we say something like, okay, I'm going to add silver nitrate. Well, that has nothing to do with this. But we know that silver nitrate is soluble, and silver halide ions are insoluble. So by adding silver, we are in effect removing chlorine. That is a way to say, okay, I'm going to remove my chlorine ions. Those chlorines are now gone. I will shift right to make more. So removing things always happens with side reactions. That's also very common in acid-base reactions. If we had, to do another example, calcium hydroxide, turns into calcium 2 plus and hydroxide, 2 hydroxides. If we added an acid, well, that has nothing to do with that. But the acid will remove my my hydroxide ions. So there's always side reactions that you need to worry about. The second thing we can do with Le Chatelier is temperature. Temperature is pretty easy. You just have to remember what endo and exothermic actually means. If we had an endothermic reaction, delta H is positive. It is as if heat is a reactant. So heat plus other reactants will turn into products. If we had something that was exothermic, delta H is negative, well, that's heat coming out. Heat is now a product. So my reactants will turn into products plus some heat evolved. Now, depending on if heat is a reactant or product, you can kind of see, this is the same as concentration, how reactions will shift. For my endothermic reaction, if I heat it up, I'm adding a reactant. I'll shift right. If I cool it down, I'm removing a reactant. I will shift left. Exothermic is opposite. If I heat it up, I'm adding a product. I will shift away from the products. We will shift left. Now that's not intuitive. We think heating things up makes the reaction work. Well, sometimes reactions go backwards. So which reaction are you talking about? Exothermic reactions, if you add enough heat, you will drive it back to the reactants. If you cool it down, then we can shift to the right and make more heat because you're removing a product. So those can be tricky. You have to decide if it's exothermic or endothermic, and what that means is heat being consumed as a reactant or produced as if it were a product. A couple more here. The next one is pressure scenarios. If we had pressure changes, we need to count the moles of gas. And when we do that, what we're really talking about here is counting the coefficients on the products and reactant side. Okay, counting the coefficients. Because then we know how the system will shift. So if we had a balanced equation that had 3 moles of gas on the reactant side and it turned into 2 moles of gas on the product side, now we have a difference, and we say, okay, the pressure goes up. Well, how can we bring the pressure back down? If the pressure is going up, that's more collisions. To relieve those collisions, we can make fewer molecules and shift to the right, because there are less molecules over here, so if I have products, that will make fewer collisions and bring the pressure back down. If we were in a container where the pressure was lowered, well, now I have fewer collisions. I need to bring that pressure back up, and we could do that by shifting to the reactant side. If I make more molecules, that pressure will come back up to where it needs to be. So it's always this opposite game, this undoing of what the stress that was done to the system. And if you understand pressure, this next one is really just a subcategory of pressure. It's volume changes. Because if you remember from gas laws, those are just opposite the pressure. So a volume problem is not really a volume problem. It's really a one step removed from a pressure problem. If the volume of a container were to increase, that is a sly way to say that the pressure is really just going down. So now you just handle it like you would any pressure decreasing problem. If the volume of the container were going down, volume goes down, there are more collisions, there's more pressure. That is our sly way to say the pressure is going up. So what would you do for the pressure to go up? We shift to the side that has less gas molecules. And those are really the ways we handle Le Chatelier problems. Now they might combine all of these things. Once you know you have Le Chatelier problems, let's say you already reached equilibrium, you have all your concentrations in whatever category you want. They could say, okay, now we've got this Le Chatelier thing. I'm going to add more of this and shift right or left. Well, we could use our X values and calculate these new concentrations, or it could just be conceptual problems. Is this going to increase or decrease? How will it affect the constants, etc.? It's important to note that equilibrium constants are constant for these Le Chatelier shifts. They are constant except at temperature dependence. Temperature shifts will change equilibrium numbers. So if we have more products, the K value will actually increase. If we have more reactants, the K value can actually decrease. Those can change for temperatures. And then we'll wrap up equilibrium part 2 with acids and bases in the next video.